All right, we've got the basic language down. Now, let's talk about the data itself. And here's something that genuinely surprises a lot of students. The type of data you have actually determines what kind of analysis you can do. You can't just take any kind of data and plug it into any formula. So in this section, we're going to learn how to recognize the different types of data and how to tell them apart. This may seem simple at first, but it's going to matter again and again throughout the rest of the course. So this is definitely one of those topics that pays off later. Okay, so the very first split we need to understand is qualitative versus quantitative data. Let's take them one at a time. Start with the left side of the slide. Qualitative data, which we also call categorical data, is made up of categories, labels, or names. It's not the kind of data where doing arithmetic really makes sense. Think about Netflix, for example. The genre of a show, drama, comedy, science fiction, that's qualitative data. Your subscription tier is qualitative. The device you watch on is qualitative. Your eye color, your car brand, your blood type, all of those are qualitative. And here's a simple test you can use. Try doing math with it. Can you calculate the average of drama and comedy? No. Drama plus comedy divided by 2 doesn't mean anything. That's a pretty good sign that you're working with categorical data. Now look at the right side of the slide. Quantitative data is numerical. These are actual numbers that we can measure, compare, and calculate with. Take the iPhone example. The screen size is 6.3 inches. The weight is 199 grams. The price is $999. All of those are numerical measurements. And here's the important difference. With quantitative data, arithmetic actually means something. I can say that phone A weighs 50 grams more than phone B, and that statement makes sense. I could also calculate the average price of several phones and get a meaningful answer. So here's the quick way to keep the two types straight. If it's a label, a name, or a category, it's qualitative. If it's a number where doing arithmetic actually makes sense, it's quantitative. Simple as that. Now, within quantitative data, there are 2 more types we need to separate. And this distinction matters later when we start graphing and analyzing data. So let's look at both sides of the slide. On the left, we have discrete data. Discrete data is data that we count. It comes in separate, distinct values, usually whole numbers, with nothing in between. Look at the Spotify example. You played 12,547 songs. You listened to 432 artists. You created 23 playlists. And here's the key. You can't play a song 89.5 times. You can't create 23 and a quarter playlists. Those values move from one whole number to the next. That's discrete data. Think countable. Now look at the right side. Continuous data is data that we measure. It can take any value within a range. And in theory, it can be divided into smaller and smaller values. Take the smartwatch example. You walked 3.47 miles. Your heart rate is 72.3 beats per minute. You slept 7.35 hours. And here's what makes this continuous. Between 72.3 and 72.4, there is always another possible value. There could be 72.35 or 72.351. And we could keep going. The only real limit is how precisely our device can measure. That's continuous data. Think measurable. Now, I have to warn you about one example that trips up a lot of students. Money. Is money discrete or continuous? Technically, money is discrete. That's because it usually only goes down to the cent. You can have $10.23, but not $10.23.7. But in statistics, we usually treat money as continuous. Why? Because money can take on so many different values, and we often do calculations with it, like finding averages. So here's the practical rule. Unless a problem specifically tells you otherwise, treat money as continuous. Don't overthink it. So really, the heart of this distinction is simple. Discrete means counting. Continuous means measuring. Okay, now we're going one level deeper. And I'll be honest with you, this is one of the most important ideas in the whole chapter. So stay with me. Even among different types of data, there are 4 levels of measurement. And the way I want you to picture them is like a ladder or a staircase, which is exactly how they're shown on the slide. Each level can do everything the level below it can do, plus one more thing. So they build on each other. Let's start at the bottom rung. Nominal. Nominal data is made up of named categories with no natural order. Think about dog breeds, eye color, or zip codes. With nominal data, all we can really do is count how many observations fall into each category and find the most common category. There is no ranking. A golden retriever isn't higher or lower than a poodle. They're just different categories. Now step up to ordinal. With ordinal data, we can put things in order. We can rank them. But here's the catch. The gaps between the categories are not necessarily equal. Think about star ratings, education level, or t-shirt sizes. A 5-star review is better than a 4-star review, sure. But is the jump from 1 star to 2 stars exactly the same size as the jump from 4 stars to 5 stars? Not really. It's a little fuzzy. So with ordinal data, we can rank the values, and we can find things like the median. But we cannot assume that the spacing between categories is consistent. Now, let's step up again. Interval. With interval data, the gaps are equal, but there is no true zero. The classic example is temperature in Fahrenheit. The difference between 40 and 50 degrees is 10 degrees. And the difference between 70 and 80 degrees is also 10 degrees. So the spacing is consistent. But 0 degrees does not mean there is no temperature. 0 is simply a point on the scale. It does not represent the complete absence of temperature. And because the intervals are equal, we can do more mathematically. For example, at this level, calculating a mean or an average makes sense. IQ scores and calendar years are also common examples of interval data. And finally, at the very top of the ladder, we have ratio data. This is the most flexible level of measurement. Ratio data has equal intervals, and it also has a true zero. That means 0 actually represents none of the quantity being measured. Think about salary, height, weight, age, or speed. $0 really means no money. 0 pounds really means no weight. And because ratio data has a true zero, all of our basic arithmetic operations make sense. We can add, we can subtract, we can multiply, we can divide, and we can make statements like twice as much or 3 times as fast. Those comparisons actually mean something. So the 4 levels are nominal, ordinal, interval, and ratio. Learn them in that order, because each level unlocks one more thing you're allowed to do with the data. And if this doesn't completely click yet, don't worry, that's normal. The next slide is going to give you a cheat sheet that makes the whole structure much easier to see. Okay, so this slide is basically your cheat sheet. And this is definitely one worth taking a screenshot of, because it sums up that whole ladder in one table. Here's how to use it. To figure out the level of measurement for any data, you can ask yourself 3 questions. And they're the 3 columns you see here. Question 1, can you rank it? Question 2, are the intervals equal? And question 3, is there a true zero? Those 3 questions will usually tell you exactly where the data belongs. Now, let me show you why this actually matters. Because this is not just vocabulary. Knowing the level of measurement can stop you from doing something completely meaningless. One of my favorite examples is zip codes. Imagine someone collects zip codes from a group of people and then calculates the average zip code. Technically, you'll get a number, but that number means absolutely nothing. Why? Because zip codes are nominal data. They look like numbers, but they're really just labels. So averaging them makes no sense. That's the habit I want you to build. Before you run a calculation on data, stop and ask, what level of measurement am I working with? Because the level tells you what kinds of calculations actually make sense and which ones do not. All right, so now we know how to classify our data. The next big question is, where does that data come from in the first place? And how do we design a study so we can actually trust the results? That's where we're heading next.